Hey everyone, Mr. Hauk here. In today's videos, we're going to be looking at hyperbolas. So we learned previously that an ellipse can be defined as the set of all points xy, such that the sum of the distances between those xy points and two fixed points called the foci are constant. A hyperbola can be defined as the set of all points xy such that the difference of the distances between those xy coordinates and two fixed points, again the foci, is constant. Geometrically speaking, a hyperbola is created when a plane intersects a double-napped cone at an angle such that both halves of the cone are intersected. And we can see that right here in the diagram. So we've already covered circle, we've covered ellipse. Now that we're looking at hyperbolas, notice that we have this double-napped cone, and the plane is cutting through the cone in such a way that it's cutting through both parts of the cone, both sides of the double-napped cone. And it's creating this kind of a shape right here. Okay, that kind of a curve. So that's what we're going to be investigating here with these hyperbolas. So, similar to with ellipses, it'd be beneficial for us to interact with this definition of a hyperbola. So once again, I've linked into the notes here an interactive graph for a hyperbola. So let's give that a look real quick. So here's our interactive hyperbola. And notice that we have this point P on the parabola in pink, and the two foci are the points A and B. So notice that line segments are being created between P and A and P and B, and if you look at the difference between PA and PB, the difference is 2. And no matter where I move this point, even though the distances between the point in A and B are going to change, notice that the difference of the points, or the difference of those line segments, is always remaining a 2. And you can see that right there with PB minus PA. So now that we've seen how a parabola is defined, let's explore some of the parts that make up a parabola. Similar to ellipses, each parabola has two axes of symmetry. We call these the transverse axis, which passes through the center and contains the vertices. So here, this is our transverse axis that I've highlighted in red. Notice the endpoints of the transverse axis are the vertices, and the vertices are on the hyperbola. Okay. Here in red, this is our hyperbola. So the transverse axis connects the vertices, goes through the center. The conjugate axis passes through the center as well and contains the co-vertices. So here's our conjugate axis, and it contains the endpoints are the co-vertices. The center of the hyperbola is located at the intersection of the transverse and the conjugate axes. We can see that right here. Transverse axis, conjugate axis. We see the center is the intersection right there. Now, every hyperbola also has two asymptotes that pass through the center. As the hyperbola moves away from the center on each side, its branches approach but never touch these asymptotes. Think of your asymptotes from algebra when you dealt with exponential functions. We know an asymptote is a line that a curve can approach but never touch or pass through. So hyperbolas have these asymptotes that are passing through the center. The intersection of the asymptotes is also the center. And then notice that the curves that make up the sides of the hyperbola approach but never quite touch these asymptotes. So when we look at these graphs here, there's a lot of different pieces going on. We have our center, our vertices, our co-vertices, and all of these together kind of make what we call the central rectangle right here. Okay, this is called the central rectangle. And if you look at the asymptotes connect the diagonals of the central rectangle, and they pass through the center as well. And these asymptotes are what guide the curve that make the curves that make the hyperbola on each side. And again, notice that the hyperbola is never touching the asymptotes, but is always approaching the asymptotes as the curves move and branch away on each side from the center. So it turns out that deriving the equation of a hyperbola can be pretty messy. For those interested, there's a link here below, right here. If you want to check out how the equation, specifically the hyperbola equation centered at the origin, If you want to check out how that is derived, click on that and you can see the derivation of that equation. But let's jump into the equation. So in general, a hyperbola has the equation ax squared plus by squared plus dx plus ey plus f equals 0. And the thing is, though, is that for a hyperbola, either a or b is going to be negative. So, you might see it written sometimes as like ax squared minus by squared plus dx plus ey plus f equals 0. Then another version could be negative ax squared plus by squared plus dx plus ey plus f equals 0. But we can see, here the x, so it should be x squared. Here the x squared is negative because a is negative. Here the negative by squared, so the y squared is negative because of the negative by, or the negative b rather. So that's what you need to know when looking at the general form. Either the a or b is negative, but not both. But versus, if you looked at ellipses, the x squared and the y squared were both positive. Same thing with circles. The x squared and the y squareds were both positive. But with hyperbolas here, one of the two is going to be negative. And that brings us to the standard form equations. So just like with ellipses, we have two different types of hyperbolas. We have hyperbolas that can open to the left or right. So notice the curves that make up a hyperbola are opening left and right. Or we can have hyperbolas that open up or down, such as this example here that I'm highlighting. Depending on the type of hyperbola you have is going to change the equation that you end up using, the standard form equation. So notice that for a hyperbola that opens left or right, the x is on the left side. The x comes first. The y is coming after the minus sign. For a hyperbola that opens up or down, like this hyperbola, notice that the y is coming first and the x is after the negative sign. So that's how you're going to see, if you're given an equation, you want to figure out what's the direction of opening for my hyperbola. You look at the equation and you say, okay, which one is coming first in standard form, which one is going after the negative sign. And that's going to help you determine, x first opens left or right, y first opens up or down. The other thing that's very different about hyperbolas, when we looked at ellipses, we always had that a was bigger than b. For hyperbolas, a is always going to be the denominator on the left side, okay? So now a is not going to be bigger than b all the time. Sometimes a will be bigger than b, sometimes b will be bigger than a. And also sometimes a can equal b. There's also that case as well. So, when working with hyperbolas, don't think a is always bigger than b like we did with ellipses. Just think, okay, a is going to go on in the denominator on the left side that comes first, okay? But just like with ellipses, we have a set of formulas for the different types of hyperbolas. So let's say that we're dealing with a hyperbola that opens left or right. Then we have a set of formulas right here that can help us find all the different coordinates that we're worried about. So notice, for a hyperbola, remember we said the transverse axis is the axis that connects the vertices, and the vertices are the actual points on the hyperbola. So the distance from the center to the vertices on each side, we call that a. And that's the same for either a hyperbola that opens left or right, or also a hyperbola that opens up or down. Regardless of the kind of hyperbola that we have, the distance from the center to the vertices is always going to be a. So we can see that to calculate the transverse axis is just going to be 2 times a, regardless of what kind of hyperbola we're dealing with. Same thing for the conjugate axis. So b is always going to be half the distance of the conjugate axis, again, regardless of which type of hyperbola we're working with. And that's how we can find the distance or the length of the conjugate axis. It's going to be 2 times the b value. And again, b being the distance from the center to a co-vertex. And then we start to get into the kind of specific formulas for the 2 types of hyperbolas. So we can see the vertices for a hyperbola that opens left or right is going to be different than the vertices for a hyperbola that opens up or down. When you're working through your problems, you want to make sure that you identify the kind of hyperbola you're working with first before you start working with the different formulas. Okay. Another key difference that we want to talk about with hyperbolas is the C term. So the C term is still going to be the distance from the center to a focus, but notice that with these hyperbolas, the focus points, the foci, are located here. For a hyperbola that opens left or right, here's the foci. For a hyperbola that opens up or down, here's the foci. And but the C term is still the distance from the center to that focus, regardless of the kind of hyperbola you're working with. But notice that this time, the C term is bigger than the A term. With ellipses, when we had an ellipse, the C term was always smaller than the A term. But with a hyperbola, the C term is always going to be larger than the A term. But what that means is that the equation we use to calculate the C term is going to be different. This time, the equation, instead of being c squared equals a squared minus b squared, the equation will be c squared equals a squared plus b squared. So to calculate c, we're going to have c equals the square root of a squared plus b squared. The other thing that we have to worry about with hyperbolas that we didn't have to worry about with ellipses are the equations of the asymptotes, since hyperbolas now have these asymptotes. Now here on our in our notes, we're going to represent the equations of the asymptotes in point-slope form, and the equations of the asymptotes can be found right here. And again, they're going to be different depending on whether you have a hyperbola opening left or right versus a hyperbola opening up or down. And then similar to ellipses, we also have the eccentricity. Again, eccentricity being E equals C divided by A. And that's for both types of hyperbolas. Okay. Something also to notice about hyperbolas, when we think about, ellipses, we would have had the vertices and the co-vertices, and that would have helped us sketch the graph of the ellipse, right? Well, notice that for a hyperbola, it's almost like we took the ellipse and we kind of flipped it inside out to get this graph instead, okay? And you can see just from the definition of ellipse and hyperbola that ellipses and hyperbolas have nearly identical definitions. One is dealing with the sum of, all those points x, y, and the distances between them, between the foci, and the hyperbola is dealing with the differences. So ellipses and hyperbolas very much very closely related to each other, but some obvious key differences. All right, so let's try some practice problems. I'm going to erase all this real quick so we have some space to write. All right, so in our first example, we're going to be given the equation of the hyperbola in standard form, and we want to find all the following characteristics. We want to find the center, the vertices, the co-vertices, the foci, the eccentricity, the equations for the asymptotes, the length of the transverse axis, and the length of the conjugate axis. So we have a lot of different parts that we want to worry about finding. I'm going to go ahead and section this off just to kind of keep myself organized as I work. And let's go ahead and get started. So first things first, let's determine whether this hyperbola is going to open up or if it's going to open down. So we look at our equation and we notice on the left side, the variable that's coming first is y. If y is the variable that's coming first and x is the variable that's following the negative sign, then that means the hyperbola is opening up and down. So I'm going to take note of that first. This hyperbola opens up or down, or opens up and down. And again, we saw that because y is first in standard form. Okay. So the next thing we're going to need to do is we're going to need to figure out what A, B, and C are. Because if you look at, again, just like with ellipses, if you look at your equations, the equations and all the different formulas require A, B, C, and the center HK as well for many of them. So we need to identify the center, which we're going to do here in a moment, but we also need to go ahead and find the values of A, B, and C. So let's dedicate a little bit of time to doing that. A, and again, remember, I'm going to put this up here, and I actually have it up here already. A very important note for hyperbolas, A is not always larger than B. This time, A is always going to be the denominator, or coming from the denominator, that comes first. Okay, so A is going to be the square root of the first denominator. So A is going to be the square root of 9, which is 3. B is going to be the square root of the second denominator. Second denominator is 16. Square root of 16 means that B is going to equal 4. And C, remember that for hyperbolas that we just went over a moment ago, C now has a different equation. Now that for hyperbolas, C is a longer length than A. So C is going to be the square root of A squared plus B squared. And in this case, A squared plus B squared, that's going to be, let's erase this real quick. Square root of A squared plus B squared is going to be the square root of 9 plus 16, which is the square root of 25, which for us works out pretty nice because that's going to be 5. So we can see that our A term is 3, our B term is 4, and our C term is 5. And just real quickly again, reminding ourselves what these different values mean is always important. The A term is the distance from the center to a vertex. If we double the A term, we get the length of the transverse axis. The B term is the distance from the center to a co-vertex. If we double this length, we get the length of the conjugate axis. And the C term is the distance from the center to a focus point on either side. Okay. All right, so let's start looking at the different values here. We'll start with the center. The center of this hyperbola, well, we know the center is h comma k. Now here's something that can be that can get students sometimes. You know, you're so used to having the x on the left side and the y on the right side that some students might automatically look at this and say, okay, well the center is going to be change the signs. Center is going to be 2, -1, and just because they're so used to seeing x on the left side first. But with hyperbolas, y can be on the left side and x could be on the right side. So when you're looking at the center, remember that coordinates are always x first, then the y value. So the center in this case, since x is over here, the center is going to be -1, +2. Okay, so make sure that you're a little careful with when calculating the center of a hyperbola. Now let's look at the vertices. So we've already identified that this is a hyperbola that opens up and down. Let's look at the equation for up and down and all the different formulas. So here we go. We can see this hyperbola opens up and down. We want to find the vertices, so we come down here to this section, and the coordinates of the vertices are h, comma, k plus or minus a. So h, comma, k plus or minus a. We have all those pieces already because we know that the center, which is hk, we know h is -1, we know k is +2, and we've already calculated that a is +3. And again, we see that we have this plus or minus sign because we have 2 vertices here. Let's go ahead and calculate both coordinates, one with the plus sign, one with the minus sign. And this is going to give us -1, and then 2 plus 3 is 5. And the coordinate for the other vertex is going to be -1. And then let's see, 2 minus 3, that's going to give us -1. And here's the coordinates for our vertices. And again, if we connected the vertices here, if we drew a graph and connected them, we would have the transverse axis. All right, the co-vertices. Very similarly, let's go ahead and go to, since we're dealing with a hyperbola that opens up and down, let's go look at that section for those formulas. Co-vertices are going to be h plus or minus b, comma k. So h plus or minus b, comma k. And let's plug in the values. Again, we know h is -1, plus or minus. We found b was positive 4, comma k, which is 2. And again, plus or minus sign, let's calculate both co-vertices. Negative 1 plus 4, that's going to be 3, 2. And then negative 1 minus 4, that's going to give us negative 5, comma 2. All right, foci, same deal. Let's go look at our formulas for up and down hyperbola. The equation for the foci, or for the two focus points, is h comma k plus or minus c. So h comma k plus or minus c. And again, let's just do what we've been doing for a while now. So h is negative 1, k is 2, c is 5. Calculating both focus points, we get negative 1, 2 plus 5 will be 7. And we're going to get negative 1, 2 minus 5, that's negative 3. So negative 1, 7, and negative 1, 3. I don't like that. I want the box that gets shaded in. There we go. All right, the eccentricity. Eccentricity, same formula from ellipses, c divided by a. C is 5. A we calculated to be 3. Yep, right there. And notice that with hyperbolas, that since the c term is always going to be bigger than the a term, for a hyperbola, the eccentricity is always going to be bigger than 1. Okay, because the numerator will always be larger than the denominator. 5 over 3, let's round that, or not round it, but rather approximate as a decimal, and that's about 1.667, if we round to 3 decimal places. All right, the asymptotes. So equations for the asymptotes for a hyperbola that opens up and down, it's going to be y equals plus or minus a divided by b, comma, or not comma, but rather parentheses, x minus h plus k. And once again, we're just going to plug in the values that we know. So this is y equals plus or minus a over b. We know a is 3, b is 4, so this is plus or minus 3/4. X minus, well, h, we have h is negative 1. So if we do minus negative 1, that's just going to be a plus 1. So this would be x plus 1. And then we have plus k, so we just take the k value, add it on, so plus 2. This equation for the asymptotes, you have to be just a little bit careful with your center, h and k. Notice that in this equation, the h, or the x-coordinate of the center, is getting changed because of the negative in front of the h, but the k value of the center is not getting changed when you plug it in because it's just plus k. K isn't getting altered by a negative sign. Okay, so make sure that you are a little bit careful with that when you're going to plug in your pieces. All right, next, length of the conjugate axis and length of the transverse axis. Well, the nice thing here is that the length of the transverse axis is always 2 times a. Since we don't have to worry about with hyperbolas, which is larger, a or b, or we don't have to, a isn't always going to be bigger than b, we know that a is always just coming from the first denominator. And the length of the transverse axis is always going to be 2 times a. So here we have 2 times a, that's 2 times 3, which is 6. We'll say 6 units because this is a length. Similarly, with the conjugate axis, the length of the conjugate axis will always be 2b, regardless of whether we have a hyperbola that opens up or down. So 2 times b, that's going to give us 2 times 4, which is going to be 8 units. And remember that the conjugate axis connects the co-vertices together, while the transverse axis connects the vertices together. Okay, so very similar to ellipses. You just have to, some key differences. Again, remember that for hyperbolas, a is not always larger than b. That's pretty important. For hyperbolas, you want to determine the direction of opening. Does it open up and down versus left and right? And again, that's going to be determined from what comes first. If y comes first, it opens up and down. If x were to come first, it would open left and right. Okay, And then just once more, once you've determined the direction of opening, you know which set of formulas to use from the page before this in the notes. Now, let's look at an example where we're going to convert from general to standard form and then use all that same information to go ahead and do some, to calculate some coordinates for the vertices, co-vertices, all that fun stuff. So here we have our general form equation for the hyperbola, 9x squared minus 4y squared plus 18x minus 16y minus 43 equals 0. Once again, remember, we can tell, if I was just looking at this and asked to, if I ask you just from the equation itself, how do I know it's a hyperbola? Remember from earlier, we said that in the equation, it's a hyperbola if either a or b, which are the coefficients of x squared and y squared, if either a or b is negative, either one of those, then we know that we're going to have a hyperbola. As we can see right here, negative 4 for the y squared, we know this is hyperbola, not an ellipse, because the equations look very similar. But let's go ahead and convert from general form here to standard form so that we can start calculating all these different pieces here. All right, so completing the square is how we're going to go from general form to standard form, just like with ellipses, just like with circles. Let's go ahead and start collecting the x variables and the y variables together. Now, what you want to do, though, is, because remember, if you look at the equations for hyperbolas, either x can go on the left or y can go on the left. The way that you determine which one is going to go first is by which one is positive. Is the x positive or is the y positive? Because notice that for hyperbolas, again, one of them is going to be negative. So the one that is negative is going to go second when we start grouping our variables. So in this one right here, notice that x is positive, so we're going to collect the x terms first on the left, and we'll collect the y terms second. So we have 9x squared plus 18x minus 4y squared minus 16y. Now let's go ahead and move the constant over, set it equal to 43. All right, so for completing the square, we know that we want the coefficients of the squared variables to be a 1. So for x squared, I'm going to factor out the 9. And we're also going to factor out the 9 from 18x. This gives us x squared plus 2x. And again, I'm going to leave a little blank here since we're completing the square. We know we want to put a constant there. For the y variables, we know we want this to be a positive 1, so we need to factor out the entire negative 4. So minus 4. If we factor out negative 4 from negative 4y squared, we just get y squared. If I factor out a negative 4 from a negative 16y, I'm going to get a plus 4y. Right, then on the right side equals 43. Now let's go find those constants that's going to make the completing the square process work. So here, x squared plus 2x, the constant that will make this work is a plus 1. Again, if you don't remember how to find that constant, you look at the middle term, cut it in half. Half of 2 is 1, and you multiply that number times itself, and that's the constant you'll put right there. Okay. Now remember that we also have to keep the equation balanced. If I put a plus 1 here, notice that it's getting multiplied by the 9 that we factored out. So to balance the left side of the equation with the right side, we have to add 9 times 1 to the right side. Here with the y variables, half of 4 is 2. 2 times itself is going to give me this constant here, which should be a 4. Now on this side, this positive 4 is being multiplied by the negative 4 on the outside, so we have to add on the right side of the equation negative 4 times 4. All right, so continuing to simplify here, we can see that x squared plus 2x plus 1, this is going to be x plus 1 times itself, with the 9 on the outside. The y squared plus 4y plus 4, this is going to be y plus 2 times itself, y plus 2 times y plus 2. And for these constants right here, 43 plus 9 minus 16 is going to give you a 36. Continuing to simplify, x plus 1 times itself, that's just x plus 1 squared, minus 4, same deal here, y plus 2 times itself is just y plus 2 squared, equals 36. All right, so going to write the standard form equation here, just like with ellipses, notice that in standard form, the right side needs to equal 1. So just like with ellipses also, let's go ahead and divide each side of the equation by this right side constant. So let's divide each side of the equation by 36. After doing some simplifying, 9 over 36, that's 1/4. So this becomes x plus 1 squared over 4 minus 4 over 36, that's 1/9. So this is y plus 2 squared over 9. And then, of course, 36 divided by 36 equals 1. All right, so now we have our hyperbola in standard form. X plus 1 squared over 4 minus y plus 2 squared over 9 equals 1. And since we can see that the x is on the left side, x is coming first, this also means that this hyperbola opens left and right. And again, that's going to be extremely important for us because that's going to determine which set of equations or which set of formulas we use when finding all the key characteristics here in just a moment. All right, so we also know that in addition to finding the direction of opening, we're also going to need to find the A term, the B term, and the C term. So A, square root of the first denominator on the left. So A is going to be the square root of 4, which is, in this case, 2. B, the square root of the second denominator on the right side, so square root of 9, which is 3. And then C will be the square root of A squared plus B squared, which will give us the square root of 4 plus 9, which is the square root of 13. So A is 2, B is 3, C is the square root of 13. And with that information, now we can complete the rest of the problem just like we did in the problem beforehand. Just again, make sure that you're using the left and the right opening standard form equation for hyperbola when you're calculating. At this point, I would encourage you to pause the video and try to find all those key characteristics below. When you're ready, unpause it here because I'm just going to scroll down and show the answers, okay? So here's all the different points. Hopefully this is what you got. If you need to, pause the video so that you can write these down. But the calculations were done exactly like in the previous example.